Welcome back, everyone. In this video, we're going to finish looking at ebook chapter 7, lesson 4, and we're going to look at resonance structures, what they are and how to draw them. Let's first start by taking a look at the Lewis structure for the nitrate ion. Go ahead and pause the video and see if you can draw out a correct Lewis structure. Welcome back. So for nitrate, hopefully the first thing that you did was to write out the molecular formula. Now, nitrate is a polyatomic ion that you should know. So you should know that its molecular formula is NO3-. After you do that, we want to count up the number of valence electrons. So there are 5 valence electrons from nitrogen, plus 6 times from each oxygen, plus 1 due to the negative charge on the ion. That gives us a total of 24 valence electrons. Now, what we do next is we put the least electronegative element in the center. That's going to be nitrogen. And we draw single bonds between the nitrogen and each of the other elements. Then, noting that we've used 6 electrons, we have 18 electrons left over. We need to distribute these remaining 18 electrons to satisfy the octets of all the elements. Start with the exterior atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, we've used up all the electrons. The oxygens, note, have each 8 electrons, so they're satisfied, but the nitrogen is not satisfied. So in order to satisfy the nitrogen, we need to make a double bond. The reason is because we need for it to share 2 more electrons or have 2 more electrons, and we don't have any left to give it, so we have to share. So we need to take 2 electrons from a nitrogen and give it to from the oxygen and give it to the nitrogen. Now, you may ask, which one do we take from? Do we take from, let's label them A, B, and C. They're all equivalent. So actually, we could have drawn a double bond going between nitrogen and any one of these. Let me show you here on the next page. So let's say that we have a double bond between nitrogen and the oxygen that is on the left. Again, we'll call these A, B, and C. It turns out that we cannot accurately represent what's going on here just by one Lewis structure. That is because we could have drawn the double bond between any of the 3 oxygens and the nitrogen. Furthermore, this Lewis structure that we have shown here represents nitrate as having 1 double bond and 2 single bonds. Therefore, it implies that there is a short bond and 2 long bonds. However, experimental data show that all 3 of the nitrogen-oxygen bonds are the same length. In fact, we can draw 3 different resonance structures to show the double bond being in between any one of the oxygen and nitrogens. And any one of these we could have drawn. So we need to account for this idea, the fact that we could have drawn it one of multiple different ways, yet they are all still valid. So this is what we call resonance. And resonance is when we have multiple representations of Lewis structures that are correct and that differ only in the positions of the electrons. The arrangements of the atoms and the total number of atoms and electrons must stay the same. So you'll notice that each of these are still nitrogen with 3 oxygens, and we can label them ABC, ABC. The number of electrons are the same, the number of atoms are the same. However, we can see that there is a difference, and that's what we call resonance. So resonance has an effect on the overall structure. And that's because resonance structures are just one perspective of the actual molecule. They don't add up to, they don't tell us the full story. So in order to understand the full story, we need to average and blend together the various resonance structures. So the real molecule of nitrate doesn't look like any one of the three nitrate drawings, but rather the average of the three of them. And we use dotted lines to represent electrons that are delocalized between the resonance structures. So these electrons that are in the double bond up here in the structure on the left are really also spread throughout the entire molecule. And so it turns out that the molecule doesn't have a full double bond, but really a partial bond. And so these dotted lines represent partial bonds. Again, this is because resonance is going to average the bond order, length, and strength. Let's take a look at this quantitatively. So if we want to take a look at the bond order of the nitrogen-oxygen bond, that's a single bond, that's a bond order of 1. The double bond has a bond order of 2. But what about the bond order of the actual structure? Well, to calculate the bond order, what we want to do is we want to sum together all of the bond orders for the two elements in question and divide by the number of resonance structures. So let's pick any two elements and look at their bond order. Let's say that we're looking at the nitrogen-oxygen bond order for that one, the one that points up. The bond order for the molecule, the resonance structure on the left is 2, on the right is, or in the middle is 1, and on the right it's 1. And there are 3 total resonance structures. That means our bond order is 4/3, or 1.33. So what is the effect on bond strength and bond length? Well, we know that as the bond order increases, so does bond strength. And as bond order increases, bond length decreases. So resonance, because it's averaging over between the high and the low bond orders, it ends up with an intermediate value, both for bond strength and bond length. Now, let's say we wanted to determine the formal charge of the oxygen atoms. In the resonance structures, it looks like they have different formal charges. But remember, the real structure is an average of them. So the actual formal charge of the oxygen atoms will be an average of the formal charges of the other resonance structures. So if we calculate the formal charge of the average, it's going to be the same thing. The sum of the formal charges over the number of resonance structures. So the formal charge on the NO single bond is going to be -1. And for the double bond, it's 0. So we have, from left to right, formal charge of 0, -1, -1 over 3 resonance structures, which is -2/3. And so similar to bond order, we see that the formal charge is an average of the various resonance structures. So this raises the question of how do we even tell whether or not a molecule is going to have resonance? If we go back to the previous slides, when looking at drawing nitrate to begin with, we were confronted with a dilemma. And that dilemma was that we could have drawn a double bond between nitrogen and any one of the 3 oxygens. So whenever we have multiple options of how to complete the Lewis structure, that's going to lead to resonance. And what we can say as well is that, and let me rewrite this, because resonance increases the number of electrons shared, it ends up stabilizing the molecule. The reason for that is because we know that the higher the bond order, the stronger those bonds are. And so we're increasing the net bond order, we're equalizing it. And so that's going to give us stronger bonds overall. There's also an effect of the fact that the electrons themselves are being spread around over a larger area. And when you have high electron density, so if electrons are compacted close together, they tend to be very reactive. So the fact that they can spread around, that's going to minimize the electron-electron repulsions and therefore lower the overall energy of the system. All right, so here is a practice problem I'd like you to try. Go ahead and put the following species in order of increasing carbon-oxygen bond length. So pause the video and try this on your own. Welcome back. So how would we do this? Well, what you need to do is you need to draw out the Lewis structures. If you draw out the Lewis structure of carbon monoxide, you get the following. And there is no, and this is the only valid way to draw it, such that the elements have completed octets. Okay? Carbon dioxide, there's only one valid way to draw carbon dioxide, such that all elements have completed octets. Well, I guess I take that back. Notice here, you could draw it with a triple bond and a single bond, and then you have its opposite resonance form, like so. Okay, so we'll come back to this. For the carbonate ion, it has 24 valence electrons. And so you should note that as we put around the lone pairs, we could draw a double bond between carbon and any one of the 3 oxygens. Remember, if there is, oops, I can spell here. If there is a choice for an alternate arrangement of electrons, then we have resonance as a possibility. Okay, and now remember, we need to be following, whenever mandatory, follow the octet rule. So carbon always follows the octet rule. Oxygen always follows the octet rule. So if you draw a Lewis structure where one of them is violating, has too, if it's violating the octet rule, such that it has too many or too few electrons, then it does not count. Okay, that's why you can't draw a different resonance form for carbon monoxide. If you tried to draw with a double bond and then 2 sets of electrons there and 1 set here, carbon is violating the octet rule, so that does not exist. Okay, so when we look at the different structures, we can determine the bond orders for each of them. Seeing that there are 3 resonance forms for carbon dioxide, if we look at the bond order of any 2 elements, we see that the bond order, remember, is going to be the sum of the bond orders over the number of resonance structures. So that's going to be 2 plus 1 over 3, 4/3. Carbon monoxide, it only has 1 valid resonance form, so it has a bond order of 3. Carbon dioxide, you could remember, you could actually draw it with triple bond and a single bond, but then you have its opposite with a single bond and a triple bond. Either way, what we can see is that if we average the bond order, that's 3 plus 2 plus 1 over 3, which is 2. Then when we look at the bond lengths, we know that the longer, the higher the bond order, the shorter the bond. And so we can rank them as follows. Now, what if we wanted to know about bond strength? Bond strength is the opposite trend as bond length. So the longest bond is going to be the weakest bond. Okay, so at this point, we've talked about resonance structures where all of the resonance forms are the same. But in some cases, this is true, as we just saw with nitrate and carbonate. But in some cases, it's not true. Take a look at this molecule below. This is thiocyanate, and its resonance structures, it turns out, are not equivalent. Okay, a double bond between carbon and sulfur, carbon and nitrogen, is not the same thing as a single bond and a triple bond, or a triple bond and a single bond. So do these differences matter? Let's talk about it. In order to answer this question, we need to go back and discuss what we've already learned about formal charge. So let's start by having you determine the formal charge for each of the elements in this compound. So pause the video and determine the formal charge within this. Welcome back. So what's the formal charge in each case? Well, and if we look at the number of valence electrons, nitrogen has 5, carbon has 4, sulfur has 6. So when you determine the formal charge, we see that in all three cases, the formal charge of carbon is 0. For sulfur, here its formal charge is 0. Here its formal charge is -1. Here its formal charge is +1. For nitrogen, the formal charge here is -1. The formal charge here is 0. And the formal charge here is -2. So which of these is the best resonance structure? Well, remember when we talked about Lewis structures in general and determining which one's best based on the formal charge. We want to minimize the formal charges. We want the ones where the formal charges are closest to 0. So that's going to eliminate this third choice. This one is not the best, it's the worst. But what about between the other two remaining formal Lewis structures? The one that is best between those two is the one that's going to have the most favorable formal charge. So in this case, we have negative formal charges, and you want to put the negative formal charge on the most electronegative element. Nitrogen is more electronegative than sulfur, so this is our best structure. This would be second, and this would be third. There are some cases that are not so straightforward. Let's take a look here at the sulfate anion. Sulfate can be drawn, and these are not even all the resonance forms, but we could draw it with 2 double bonds between 2 different oxygens and sulfurs. And that's going to have, we see here that the formal charges here, we have -1, -1, 0, 0, and 0, versus -1, -1, -1, +1, and -1, -1, -1, -1, +2. So this is, if we evaluate these in terms of formal charge, this is the best, this is the worst. But if we evaluate them in terms of the octet rule, this is the worst, and this is the best. So how can we tell if it's going to be better to minimize formal charge or better to not violate the octet rule? The answer for Chem 110 is simple. You don't. We will not ask you to determine which of those two things is more important. If you have a structure with an expanded octet and has multiple resonance forms, either any of the forms will be accepted as valid or will give you an indication as to how to make that judgment. We might say, draw the Lewis structure that minimizes formal charge, or draw the Lewis structure that has an expanded octet. Either way, we will give you information that you need to make that judgment. You won't be asked to do it on your own. All right, that is it for this video. Thanks for watching. Have a great day.